So now I'd like to welcome Dirk Zimmermann, who is the General Manager of Extruder Experts, and he will be presenting on measuring and understanding extruder wear. Thank you, Dirk.
Thank you very much. A short presentation about measuring and understanding extruder wear. My name is Dirk Zimmermann. We are here in booth A442 if there are any questions coming up. If some details are unclear, please come along, stop by, and we'll try to help you. Now, what are you going to be viewing today? Some very short words about extruder experts, some introduction wear in twin screw extruders in general, some basic problems of wear measurements, actual examples of measuring screws, barrels, and liners. A few words about wear inspection, wear limits, and a short conclusion. Now, I would like to place first a trigger warning. You're about to see badly used, damaged parts, mechanical parts. If they are disturbing to you, that's the point to leave now. There is also a short explanation of the limitations of wear measurement in general, but there is also a presentation of some hope in the future for glooming on the horizon of measuring wear, and I promise you we will have a happy end here. We will present a solution. Now, about Extruder Experts, who we are, exactly what we do. We are a specialist for wear parts for a multitude of different varieties of twin screw co-rotating extruders. That's the very focus of what we do. We supply shafts, screw segments, barrels, and we also do wear measurements. Exactly what you need, that's our claim, because if you have to cover such a wide variety of different extruder parts, you need to clearly and exactly specify what parts do you need for your extruder. There are different generations and so on. So which parts, most importantly, which material selection, which steel selections are capable to survive your process. And we do this together with the customers, get their experience, and find out what fits your process. We do wear measurements to support that. Introduction. Wear in twin screw extruders. You know all the twin screws, and I would separate normal wear from abnormal wear. Normal wear actually is induced by the products that you are running. You have abrasive products, you have corrosive products. That's normally coming from the material that you process, and there are abnormal wear, which is a mechanical problem actually. So abrasion, I don't need to really explain what that is. Your product, highly filled polymers, glass fibers, carbon fibers, even worse, they scratch on the surface of the parts and they just eat them up. The surface is being continuously removed, and if you look at, for example, that barrel, it's like the Grand Canyon has been going inside the valley and create a huge amount of wear and abrasion. How does it look in a barrel? It's the typical kneading block grooves that you see. You will see some further examples here in the next slides too. Next kind of normal wear is corrosion. And if you see, for example, here in the barrel, there's a lot of corrosion that has eaten up the material, that continuously eats up the surface, oxidizes it, and takes it out with your product, actually. How does that also look in screw segments? It's much easier to see. You have the small pittings of corrosion. You know all of that. Coming to abnormal wear. We see this often, for example, on screw segments of when the wear of the barrel is too high, then the apex area is no longer capable to separate the two screws from each other. And what happens then is that the two screws, especially at the end, start to grow into each other. And the surface of the one screw segment scratches the surface of the second. That looks like, in this picture, it's a relatively common application in long extruders. In food extruders, we see this often, that you have this contact. That's also, for example, PVC. That part is clearly gone due to the wear of the screw towards the other screw. A different type of abrasive or adhesive or frictional wear, you can many times see in the compacting area and the melting area of the extruder. The pellets are still not molten. The screw presses outside towards the barrel, and you have a rotating screw that scratches continuously on the surface of the hardened barrel. And in the end, you will have a very high local heat stresses that result in cracks, sometimes even catastrophic, like a whole part of the liner just chips out and destroys your screw and stops your machine. Very few people know that there is cavitation also. Mostly, of course, due to the humidity in food processes where you have high pressure and high, very, very abrupt pressure drops. And this leads to cavitation that starts to eat up the surface. You may experience this when you are stripping VOCs with water, for example, in plastics. Sample of how this looks like in a real screw. Now, just some samples of what the general wear means. What are the basic problems of a wear measurement? Now, in real life, the customer expects you to measure his extruder, but you deal with a fully assembled screw, a barrel section that maybe is hot. It's a dusty and dirty surrounding. You don't have space, you don't have time because the customer wants to run the machine. And all your equipment and your people have to deal with this, to work under these conditions and end up with an accuracy of measurement, which is really difficult. So how do we do in real life measuring, for example, screws? We use a caliper. What do we measure with a caliper? Normally, the outside diameter. But the point is, where do you measure? Do you measure at the start of the screw segment, in the middle, at the end? What really reflects the wear the best? But there are some geometries that you are not capable to measure with a caliper. Single flighted segments, very high pitches. You cannot use it. Now, what else you cannot measure? Inside diameters. You don't measure. What about different wear profiles, like in the adhesive contact area, the profile damages that result from that? It's a relatively limited method to measure wear. It's very simple, maybe too simple, but with some experience and the visual inspection, you can end up having an okay result. Measuring barrels and liners, coming to a point that is quite difficult because you are dealing with very deep, long black holes here. You have a fully assembled machine. If you separate the barrels, you know, the problems are getting much easier to be solved. But you have to run your measurement equipment into like a 56D L/D machine, which is becoming a real big job. So how do accurately measure these deep holes? Few words towards typical wear of barrels. You have normally the red sections at the 3 and 9 o'clock area of the extruder, because you have the contact from the rotating screws, and the apex area. These are the typical areas of wear. But you have a specific problem in twin screw extruders, because you have the interlaced bores, and you are missing out the wall. And it's about 70 degrees on that side that you are missing. You cannot measure a diameter. So in total, you end up having only like 60% of the circumference of the bore being measurable. How do we measure in real life? It's the old method. You have a digital micrometer, you have a kind of an extension piece, and the measuring head, and you can rotate it to at least, you know, try to measure the resulting diameter. But imagine you have to do this in 3.50 meter depth, or 2 meters even. You have to adjust, elongate and elongate and elongate, and with each elongation of the measuring system, your accuracy, you know, say goodbye to your accuracy. Now, if you only measure, for example, the blue line, you don't hit the real wear areas. And what do you achieve with this? Now, maybe a different method would be to use a 3-point inside measuring caliper, micrometer. The problem with that, these 3 measuring legs, they move continuously, simultaneously. So if you have an unwound bore, you cannot measure it. Then we developed the micro epsilon, developed the iDiam control with capacitive sensors. How this is working, you have some sensors that need to have a specific distance to the measuring diameter. You run the whole sensor carrier through your total length of the barrels, and you get some result. You normally measure on the left upper side 3 different diameters, the cross and the vertical section. There's an example of such a measuring head with a black tops are the measuring sensors. And you result at least over the length with a relatively good graph of the real wear over these crossed areas. So in this measurement, you can clearly see your feed barrel, your second, third, fourth barrel are really badly worn. And number 6, you should also start to think about changing it. But in general, the green area still is not measurable. The next hope in inside measuring such a deep hole is 3D laser scanning. You generate or you use a laser. I will not run the video because we resulted in some error here. You have a rotating laser head that you move inside the bore, and it will generate, measure a lot of different points, but still you have the problem of the missing wall. And statistically or mathematically, you can filter out diameters that the system measures above a certain range. But still, you end up in really not knowing where your center is. Yeah? That's a big problem for such a measurement method. Just some small example of how this looks like in real life. We have a barrel that has a crack, and we even have some sand inside. some detail, and it results into a data cloud, enormous amount, a huge file size, because you measure so many different points, but you can see at least the grooves. So there's some hope in this area that laser measuring inside can solve the problem of really knowing what is inside your computer, your extruder. Yeah. So, summary. Mechanical measurement is somewhat limited. The sensor, the capacitive sensor method of, for example, micro epsilon or our own system, kind of works well for the application. It's the best you can get. And 3D measurement is, giving some hope. But still, it's not really precise. So what can we do to get a better picture of the wear? Speaking of pictures, maybe pictures. So let's grab a camera and go inside and see the problems. Also, this is a video you will receive at the exit. Some small paper card, visit card. There's a QR code on it, so you can download the presentation, the videos, and so on to try it out. What do we see if we are inside an extruder? You see the cracks. You have no chance to measure them. You have to see them. You see, for example, in this area, there seems to be a new segment running because it scratched a whole area. You see the corrosion. You see the apex area that is badly damaged. You see the typical grooves of kneading blocks inside the barrels. You see the bad surface here. You can identify, for example, a bad groove inside from apex to apex where something may have stick to the screw and destroyed the barrel. You can see, for example, this is a feed barrel. It has never been changed. They only used the second barrel as new. So you have a huge gap here where, material stays, and in the end, you should not wonder about, black spots or something like that. Coming to wear limits. If we measure, if we do video inspection, we have to somehow identify at what diameter do you start to change your parts. Is it, for example, a fixed factor like 2% of the diameter of the screw segment? Is it a fixed value of like 2 millimeters? Is it to overlay a measurement of screw segments with the measurement of the wear of the barrels? It's really difficult to identify that. You have to understand your process, and at which level you can allow backflow or some kind of wear. And Adam just mentioned yesterday, if the extruder starts to purge the polymer out of the vacuum vent, it's time to change the screw segments. Conclusion: nothing's ever easy. It's a relatively complex field. We are used to we fly to the moon, or Elon Musk flies around the Earth. We are capable to measure, to define our location up to 50 centimeters of accuracy based on tiny time differences of the satellites in the GPS system. But frankly speaking, really measuring the wear inside an extruder is a big task. If you do it frequently, if you do the measurement with the capacitive sensors, if you do a video inspection frequently, you can follow and see how wear has developed in your extruder. You should do this on a frequent basis, depending on your process, of course. But you need experienced people that are capable to, verify and see the problems in the extruder. So you need people like your maintenance engineers that have a lot of experience, expertise. You need maybe the service technicians of the machine manufacturers to run such measurements. Or you need, in general, extruder experts to do this job. And if you need something like that, if you have problems with wear measurements, if you have problems with wear in general, we are here. A442, stop by and we will help you. We are extruder experts. My name is Dirk Zimmermann. Many, many thanks for your patience and your time. Thanks.